All right. Next example we have, the first example actually for this section is example 1, where we're asked to calculate the vector surface integral, which again, we should get in the habit of thinking of this as a flux. A lot of problems in this section will be worded as find the flux of f through yada yada yada. So whenever you hear the term flux, it's just referring to a vector surface integral of that vector field over that specified surface. So find the flux of f, this field, through the surface S. And the surface S, they actually give us the parameterization for it. So we have the function and we have the domain. And they want us to orient the surface by upward pointing normal vectors. So we do not actually have to type this into a computer or know what this graph or what this parameterization actually produces. So what I'll go ahead and do here is note that, well, if we're going to calculate this, we need to know, we already know what f of r of uv is, right? We can definitely calculate f of r of uv. We can just take our vector field up here, 0, 0, x, and replace x with the x component, which is u squared. The other thing we need from this theorem is we need to dot it with this quantity here. So again, one thing to keep in mind here is this is r cross ru cross rv or rv cross ru. It depends on the problem. All right? So we can always think of this as being our ds. Okay? So to get this, we will have to effectively first find our partial derivatives. So our partial derivatives will be 2u, 0, 3u squared. Rv will be 0, 1, negative 2v. We'll cross them, Ru cross Rv, and we will just see what we get. And if the normal vectors are not upward pointing, we can just go back and correct it by choosing to cross them in the opposite order. So Ru cross Rv, if we go ahead and do that cross product, we will get negative 3u squared 4uv 2u. Okay, so now a vector in 3 dimensions, x, y, z, it is pointing upward if its z component is a positive number. It's a positive value. So the z component here is 2u, and since u has a range of 0 to 1, that means that 2u has to be greater than 0 on the interval 0 to 1. So this is upward pointing. So I'm just going to go ahead and say is upward. Okay. So that means we don't have to do any corrections here. That's good. So now we can calculate our vector surface integral. So the double integral over the surface S parameterized by r of uv of our vector field 0, 0, x dot ds is equal to the integral from 0 to 1, 0 to 1, our vector field, which we had 0, 0, u squared, dotted with the appropriate normal vector that we just found, which is negative 3u squared, 4uv, 2u, and then we're integrating over a rectangle in the UV plane. The bounds are the same, so literally doesn't matter, just pick something. Do our dot product, and we have 2u cubed du dv. Well, if we integrate v we'll have v between 0 and 1, which is 1. And then if I integrate u cubed, we'll have 1/4 u to the 4th between 0 and 1, which is just a fourth. But we have this extra copy of 2, so our answer should be 2 times a fourth, which is 1/2.